All right, guys, welcome to our Unit 5 study guide. Let's go ahead and get started. For each problem, you're going to be finding the value of C that satisfies the mean value theorem. You're going to have one question like this on your test. This is a multi-point question. You get 1 point for the derivative, 1 point for finding the average rate of change, and 1 point for finding C, total of 3 points. All right, so mean value theorem. It's where we're looking for that point C where the instantaneous rate of change is equal to the average rate of change. Now, this can only apply to a function that is continuous and differentiable on the interval that we're looking at. And so technically, we usually check that to begin with, but for the problems I'll be giving you on this exam, they're all going to work because I just want to see how well you can apply the theorem, and that's it. So let's go ahead and get started here. So the first thing we're going to do is we're going to find our derivative, which would give you your first point. So make sure you have that recorded on your papers. The next thing you're going to do is you're going to calculate the average rate of change. And so to do that, we need to figure out what is y of 1 and y of negative 1. And to do that, we're going to plug 1 into the original equation. I forgot my prime here, by the way. That's a derivative. So we're plugging 1 into the original equation, and then we're also going to plug negative 1 into the original equation. And that's what will go in these top spaces here. And when I do that, by plugging in 1, I get 2, and by plugging in negative 1, I get 4. The bottom, I put the negatives together to become a plus. And so the outcome there is negative 2 over 2, which is negative 1. And that will likewise be your second point there. All right, the next thing you have to do is remember the point of the mean value theorem is that we're looking for the place where the derivative is equal to the average rate of change. And so now we have to solve this equation up here. And so here we go. Since it's a quadratic, the first thing I'm going to do is I'm going to make sure that it equals 0 by adding the 1 to both sides. And then I'm going to go ahead and factor it. You could also use quadratic formula if you're more comfortable with that. See if that works real quick, just a second. I'm going to make one little change here. That should be a minus. There you go. And then we set each one of these equal to 0 and solve. This one on the right will give me 1, and this one on the left is going to give me 1/3. Now, we only want answers that are actually on the interval that we care about. And so now, technically, both of these are on the interval. But part of the mean value theorem is that it's differentiable on the open interval. So whether or not you want to include this last one's up to you. If you're thinking of the differentiable interval, then you wouldn't include it. But if you think of the continuous interval, you would. So it doesn't matter. You can include it one way or another. I'm curious how this software, I think the software does not include both answers. It only includes the ones that are in between. Let's see, just to be sure. Yeah, it just includes the one in between. And that also makes me realize I forgot I had a missing sign here. That's supposed to be a negative, my bad. So don't include the endpoints for mean value theorem. Just do the ones that are actually in between the points. And that's probably because of the fact that the derivative is only on an open interval when you're doing these. All right. Now that's one type of problem you can have. Now I've included here 3 problems, and they're all different types of functions. Now the first one I gave you was a polynomial. Those are nice to have, in my opinion. Those are the easiest. Rational functions, a little bit more challenging, so I'll show you how to work with that, but the steps are going to essentially be the same. And then also these functions that have rational exponents, and those are a little bit tricky as well. So I want to make sure that I don't know which kind you're going to end up with on your test. So I want to make sure you're prepared for all of them. So we're going to do one of each. Okay. So same steps though. Start off by finding your derivative. We do, for these ones, low d high minus high d low. Draw a line and square below. All right, so here we're going to distribute the 2x into the parentheses, and we're going to get 6x squared minus 6x. Here we're going to have 3x squared, but it's being subtracted. On the bottom we have 3x minus 3 being squared. And for these types of problems, a lot of times I'll just leave the bottom alone, but for these types of problems you're going to want to actually work it out. So to continue here, we have 6x squared and negative 3x squared. Those can be combined to make 3x squared. And then we also have a negative 6. That's going to stay just the way it is. On the bottom, we're going to FOIL it out. So you're going to do the first number multiplied by the first number. That would be 9x squared. You can do the last number times the last number. That will also be 9. Then you're going to do the two inside numbers multiplied together, and you're going to double it. So negative 3 times 3 is negative 9, and we're going to double it to get negative 18x. Now that little trick that I just showed you, instead of using the box method or the foiling method, that works only when you're multiplying two binomials that are exactly the same. Otherwise, you have to FOIL it out like you did in Algebra 1 and Algebra 2. In any event, there is our first derivative, and our first step is concluded. Now, you don't have to do this, but you can reduce if you notice, but it only works if all the numbers can be reduced by something. If one of them don't have something, then you can't reduce. So you have to be able to divide something out of all of them. You don't have to do this step, but it can make your numbers a little bit smaller and therefore a lot easier to work with if you do. So I'm going to go ahead and divide everything by 3. And I'm going to use that as my derivative. Now, like I said, you don't have to do that, but it's an option. Okay, so there's step 1. Now we're going to go ahead and move into step 2, which is where you find your average rate of change. So we're going to do y of 4 minus y of 2 over 4 minus 2. And we find these, once again, by plugging the numbers into the original function. So let's see what we get out of that. The bottom is going to be equal to 2. And let's figure out what our two top numbers is. If I plug in 4, let's see what I get. That's what we get there. We have a complex fraction. So what I would encourage everybody to do is to multiply by the denominator. In this case, I'll start by multiplying by 9, but you have to multiply everything by 9. Now in this case, these 9s cancel, and that'll leave me with 16 on the top left. And here, on the top right, the 3 goes into the 9 also. That's nice. Leaving me with 4 times 3 on the top, which is 12. And then 9 times 2 on the bottom is 18. So that's my result from simplifying my complex fraction. And then finally, 16 minus 12 is 4. And then we can reduce that to be 2/9. So there's my average rate of change. So my average rate of change is 2/9. My instantaneous rate of change is that function there. And so we're going to set those things equal to each other now. And that's the third step. All right, now whenever we're facing a problem like this, the way we're going to deal with it is we're going to solve by doing some cross multiplication. So we're going to do bottom left times top right. And then we're going to do bottom right times top left. Set those equal to each other. And once again, we've got some quadratics here. And when you have quadratics, you want to move everything to one side so that it equals 0. So now we have negative 3x squared plus 6x plus 6. All right, now here's another situation where if you see it and you want to take advantage of it, you can. You see how all three of these they can be divided by 3, right? In fact, I don't like the negative in the front, so I'm going to divide all three of these by a negative 3, which is totally legal so long as you also divide this side by a negative 3. And that'll give me a little bit of a nicer equation to look at. You don't have to do that. You'll get the right answer even if you don't, so long as you do everything else correctly. But smaller numbers are better to work with and less likely to make mistakes with. So when you can reduce, reduce. It makes things better. All right. Well, now I already know this is not going to factor, and sometimes that happens. And so whenever you come across a problem that's non-factorable, you are going to be using the quadratic formula. The middle term goes in the first two blanks. The front coefficient goes in those two blanks, and the last term goes there. Simplifying this, we end up with 2 plus or minus the square root of, this is going to be 4, and then negative 4 times negative 2 times 1 is going to be 8. So 4 plus 8 is going to be 12 for 2. And we want to simplify our 12 here. Now, you guys, this is a free response quiz, this question, so honestly, you can just stop here if you want to on my test. I'll give you full credit. I don't care. But, you know, I do want to have you guys be reminded of these things, because if we end up taking a normal AP exam this year, meaning multiple choice, they wouldn't have that as an answer. They'll have the simplified one. So that's how you simplify a square root. You break it down into its factors and you take any pairs out. And so we have 2 plus or minus 2 square root of 3 over 3. And then if you see anything that can be reduced out, oh, not 3 on the bottom, my bad. It's 2. If you see anything that you can reduce out of all three of these, then you go ahead and do that. Now, it could be 1 plus the square root of 3 or 1 minus the square root of 3. Now, I know that the square root of 3 is bigger than 1, so if I do 1 minus the square root of 3, it's going to end up being negative, and that's not on my interval. So I know that I don't want the one that has a minus in it. I only want the one that has a plus, and that's going to be my answer, 1 plus the square root of 3. But like I said, you guys can stop up here if you want to. All right. So that's dealing with rational expressions. Let's go ahead and take a look at expressions that have rational exponents. All right, so derivatives first, right? Put your exponent in the front. Doing the power rule. Take 1 away from your exponent. And since this is also a chain rule, we're going to multiply it by the derivative of the inside, which is 7. Okay, the next thing I'm going to do is I'm going to rewrite this a little bit. First of all, I'm going to multiply the negative 2 times the 7, and I'm going to get negative 14. The 3 is on the bottom. And since this thing has a negative exponent, I'm also going to put that on the bottom. And there's my derivative. Okay. Once again, we also want to go through and we want to find our average rate of change. So that's the end of step 1. Let's move on to step 2 and find that average rate of change. So we want to do y of 4 minus y of 2 over 4 minus 2. Now when you plug 2 in here, 7 times 2 is 14, and 14 take away 14 is 0. So that whole thing right there just becomes 0, so that's nice. But this guy here gets to be a little messy. So I'll show you how to work that out. So, I mean, multiplication and subtraction, right? So 28 minus 14 is 14. Now, typically what you would do if you could is you would find the cube root of this number and then square it. You would find the cube root of 14 and then square it. But we can't, there's no cube root of 14 that's a nice number that we could do mentally. And you could do it on your calculator, you get a decimal. But I'm just going to leave my answer like this because we're going to go ahead and get rid of that cube root in a little bit. You'll see it's just going to disappear. But for now, I'm just going to leave that nasty looking thing right where it is. Don't want to deal with it. All right, and so if we simplify this, I end up with negative. Let me make some more space for myself here. I end up with negative 14 to the 2/3 power over 2. And that's my average rate of change, as strange as it looks. There it is. All right, the next thing we're going to do is we're going to set our derivative equal to that average rate of change. So I'm going to take this number here, move it right down here, and set them equal to each other. Okay, now we are going to cross multiply again, but my advice is before you cross multiply this time, let's get rid of those cube roots, those little powers that have 3's in the denominators. And the way you do that is you cube both sides. You raise both sides to the 3rd power. Okay, so when you do that, you're going to raise the 14 on the top left to the 3rd power. It'll be a pretty big number, but sit tight. We'll deal with that in a minute. You're also going to raise this 3 down here to the 3rd power. And when you raise this fraction piece here to the 3rd power, this 3 will cancel out with this 1/3, and it'll just leave you with 7x minus 14. So even though we've got these really big powers now, on like 14 to the 3rd power is going to be a pretty big number. But even though we have a really big number there, we got rid of the cube root, so that's kind of nice. Same thing on the other side. We're going to cube the 2 on the bottom. And whenever I apply the cube to the 2/3, it's going to cancel that denominator out and leave me with negative 14 squared. Okay, so that's the first thing you want to do is get rid of that little denominator in the power. Okay. Now you can do this one of two ways. You could do this by changing this into 14, like actually figure out what's 14 to the 3rd power just using a calculator. It's going to be a really big number. You can do it that way. It will work. I'm going to show you an interesting little strategy. The only downside is I'm not sure if the strategy will apply on your problem that you're going to be working on, but it does in this case, so I'm going to use it. But in any event, if all else fails, just go ahead and do the cubing. So like 3 to the 3rd is 27, right? I'm going to do that one because that's nice and easy. Okay, so now we're going to cross multiply, right? So we're going to do the number on the top left multiplied by the number on the bottom right. And we're going to do the number on the top right multiplied by everything on the bottom left. You guys will notice I still haven't done the 14 to the 3rd power. And the reason for that, we can actually just divide, is because I can just use properties of exponents when I divide this and not end up having to do as much work. Like, I don't know if that'll work out on yours the same way. It's hard to say. But if not, just do the powers and work with the numbers as usual. So first of all, double negatives cancel, right? And then anytime you do like a number to a power divided by a number to a power, you just subtract their exponent. So it's going to end up being 14 to the first power, which is just 14, right? And now this side's simplified. All right, and then we go ahead and multiply here. That's going to be 112. I'm going to distribute here. And that's going to give me the following. I'm going to go ahead and add the 378 to both sides. And then divide both sides by 189. And we end up with this. And I do believe that that can be reduced by 7. So if you divide the top and the bottom by 7, you're going to end up with 70 over 27. All right, there you go. And I don't mind if you guys just want to use calculators and stuff the whole way through. I'm okay with that. But it's nice to be able to do those things by hand as well. So. But anyway, so those are all the mean value theorem questions. And you're only going to have one of them. You're not going to be given all 3 of them. But I wanted you guys to be able to see how to do all 3 of those. All right. Let's go ahead and take a look at numbers 4 through 6. On 4 through 6, same thing. You're going to have one question. It could be a polynomial like this. It could be a rational expression like this, or it could be another one of those cube root problems. So the question this time for this set is you are being asked to find the relative extrema. And to do that, if it's a polynomial, you can use the second derivative test if you remember how to do that. But I'm going to be sticking with the first derivative test just because that one's going to work on all 3 of the problems, and I just don't want to throw too many different things at you at the moment. So first derivative test is to find any sort of discontinuities, but there are none for a polynomial. That's cool. Number 2, you want to find your derivative. Number 3, you want to find your critical values. And that is done by setting your derivative equal to 0. Or by finding where it's undefined, but my derivative is a polynomial, so it's never undefined. So for this one, I'm only going to get critical values by setting it equal to 0 and solving. Factor out a 3. And I end up with 2 values of 0 and 2. And then the fourth thing you're going to do is you're going to do that number line test. So we have 0, we have 2, and our goal is we want to plug in a number from these 3 intervals here, from negative infinity over here and positive here. We're going to plug in a number from these intervals into our derivative. I guess I should be using y, not f, because we're not talking about a function named f. We're talking about a function named y. All right, so on this interval here, I'll plug in -1. On this interval here, I'll plug in a +1. On this interval, I'll plug in 3. And we just want to see what happens with the derivative. So if you were to plug -1 into your derivative, you're going to end up with a positive slope. It doesn't really matter what number you get, but plug it in and check for yourself. If you plug it in, you'll see that you actually end up with a +9. So that means on that interval, the graph is going up. If you plug in a +1, it's going to be negative. And if you plug in a +3, it's going to be positive again. And that indicates for us that our relative max is at 0. But a max is a y value, so we're not going to put 0 as our answer. We're going to put y of 0 as our answer. That would be our relative max. and then 2 will give us our relative minimum. So y of 2 is the relative minimum. So don't just put 0 and 2. That would be wrong. The problem's asking you for the relative minima and maxima. Matter of fact, it says points. So if you wanted to be more specific, you could write it as a point where you put the x value here and the y value next to it. Now I'm being a little bit lazy here, and I give you guys full privilege to do the same thing. You don't actually need to plug it in. But what you would do is you would plug 0 into the original problem to find the y value for this one, and you'd plug 2 into the original equation to find the y value. You guys don't have to do that. Just make sure you do state it as y of 0 instead of just 0. That wouldn't be good. Now it says a point. But I really don't care. I mean, I guess for points, we better say let's write it as a point in x and a y value since that's what the directions say. Got a kitty in the background here. All right, so we're gonna do that same process now, just with some other functions. So what about rational expressions? Well, rational expressions do have discontinuities anytime their denominator equals 0. In this case, though, something a little funny happens. In the process of trying to solve this, we end up with the square root of a negative number which doesn't exist, so there's no solution to that. And what that means is that there's no discontinuities. So typically, rational expressions have discontinuities anytime the denominator equals 0, but that doesn't happen here because there's no solution that will make the denominator equal 0. So this function has no discontinuities. Now the reason why it's important to check for discontinuities is because even though we do include those in our critical value process, those can't possibly be relative extrema because there's no point there, and a relative extrema has to happen at a point that actually exists on your graph. So you do want to look for those discontinuities before you commence with the rest of the process. Anyway, step 2, we're going to find our derivative. And once again, it's a rational expression, so we're going to do the whole low d high minus high d low thing again. And don't want to forget about that negative. And you can either just leave the negative right in front, which is what I was doing before, but as you guys can tell, I keep forgetting about it. So a way that you could deal with that so you don't forget about it is just put it with the 9 on the top. That way maybe you won't forget about it. So low d high minus high d low. All right, let's simplify it. Now, back when we were doing the mean value theorem, I simplified the bottom. That'll just be a waste of your time if you do it here. So don't do it on these problems. You can. It's just that'll be a waste of your time. It won't help. Okay, there's my derivative. And step 3, we want to find our critical values. So that's where the derivative is either 0 or undefined. So where is the derivative equal to 0? The derivative is equal to 0 anytime the top equals 0. And it's undefined anytime the bottom equals 0. Okay. Now, for the one over here on the right, if I take the square root, I get this equation, which we saw at the very first step, and we already know there's no solution to that, so we'll just ignore that one. That one's not going to give me any critical values. But the one over here on the right, you would add 9 on both sides first, then you divide by 9. Now, something that I see a lot of students continually forgetting, you got to remember this. When you solve an equation by taking a square root, like right here, you need to remember that you get 2 answers. You get a plus and a minus. So there's actually 2 answers there. It's positive 1 and negative 1 when you take the square root on both sides. All right. And now we're ready for step 4. Now in step 4, even if it's a discontinuity, I would say include it on your number line test. But just remember at the end, don't count it as a relative min or a max, but it's important to put it on there, otherwise you might not pick the right numbers because it has to be on intervals of increase and decrease, and places where it's discontinuous is a place where it can change from increasing to decreasing. So you want to include those on your number line so you see all the intervals of increase and decrease, but you just don't want to put those discontinuous numbers on your number line, I'm sorry, in your final answer, because you can't have relative extrema there. But in this case, I don't have to worry about that because this function doesn't have any discontinuities, so I'm just going to use the two critical values that I have. And we're going to, once again, just plug in some numbers into our derivative that are on these intervals and see what happens. I'll do -2, I'll do 0, and I'll do 2. All right, so if I do -2, I'm going to end up with a positive slope. If I do 0, I'm going to end up with a negative slope. And if I do 2, I'm going to end up with a positive slope again. And therefore, once again, at -1, y of -1, we have a relative max. And at 1, y of 1, we have a relative min. Okay. Let's go ahead and take a look at another type of problem like this, but this one's going to be one of these types of problems. All right. So, step 1, are there any discontinuities? And the answer is no, there are none, because this is a cube root function. Now, if it was a square root, there's not a point where it's discontinuous, but they only exist on a certain interval. So you would want to look at that continuity of common functions worksheet that I've given you to know that. But in this case, it's a cube root, and cube roots don't have any discontinuities. So we're good there. Step 2, we're going to do our derivative. Saw that earlier on number 2 of our study guide here. You're going to multiply the power to the front using the power rule and subtract 1 from that power. And then you're going to multiply it by the derivative of the inside because we do have a chain rule. Then we do the top here times the top there, and that gives me a top of -8. The 3 is on the bottom. And this thing here, I'm going to put it on the bottom also. Because it had a negative exponent. And so there's my derivative. Step 3, we want to find out our critical values. And critical values are where either the numerator equals 0 or the denominator equals 0. Now the numerator can't equal 0 because it's just a number. That doesn't make sense. But the denominator can equal 0. That's the place where the derivative would be undefined. Now I want you to keep in mind the function's not undefined. The original function y is not undefined. The derivative would be undefined here. And that's okay. All right, so step 1 here is I would divide both sides by 3 to get rid of that 3. Then I would raise both sides to the third power. So if I raise this side to the third power, that's going to cancel out the 1/3. We saw that little algebraic move earlier in this lesson. And also if you raise 0 to the third power, you still get 0. So now if I subtract 12 and divide by 4, I get 3. And so I have one critical value in this case, and it's at 3. And we're going to do our trusty old number line test. So here we go. For step 4, we're going to do y prime of 0. 0 is a nice number to plug in. And we're going to do y prime of, let's say, 4. All right. And to do that, we need to see our derivative again. I erased it, so let me bring it back really quick. I believe the derivative was -8 over 3, and it was -4x plus 12 to the 1/3 power. Okay, that'll be interesting. So if I plug in 0 for x, well, this part's just going to go away. If you take the cube root of a positive number and multiply it by a positive number, you get a positive number. And if you divide a -8 by that, you're going to get a negative number. So this whole thing's going to come out negative. Now notice I didn't even try to calculate the answer because it doesn't matter. All I care about is the signs. Now if you want to get out your calculator and actually figure out an exact number, go ahead, but you don't need to. 4, if I plugged in 4, see what that would be. -4 times 4 will be -16. And -16 plus 12, that's going to come out being a -4. So by adding together the numbers inside the parentheses there, we end up with -4. Now, once again, if you want to use your calculator to figure this out, you're welcome to. But you can just know that the cube root of a negative number is negative. This is a positive, right? Right there. So a positive times a negative is negative. And if you divide a negative by a negative, you get a positive. And there we go. And so this number here at 3y of 3 is actually just going to be a relative minimum. And the reason for that is because we're changing from a negative slope to a positive slope at that point. So you'll be asked a question like that. You get 1 point for finding the derivative, 1 point for finding the critical values, and 1 point for your final answer. All right, so for this next problem, it's only a polynomial, and on your test, I'm only going to give you a polynomial version of this because to do this problem, you have to do the second derivative, and with those other two problems, doing the second derivative after the first is a little bit extra. So there's no point in doing that. We just want to make sure you know how to do the basic idea. And so in this problem, we're being asked to find the x-coordinate of the points of inflection. And also, we want to find the intervals of concavity, concave up and down. Right? So you get 1 point for finding your derivative, and you also get 1 point for finding your answer. So, first of all, we take the first derivative, which is -3x squared plus 6x. And then we're going to set that equal to 0. No, I'm sorry. We are not going to set that equal to 0. We're actually going to find the second derivative. And we set that equal to 0. Second derivative tells us about the concavity. And when we set that equal to 0 and solve, in which case I'm going to get x equals 1, that's possibly a point of inflection. It's not necessarily a point of inflection. It's only a point of inflection if the concavity changes at that point. So, number line test again, but this time we plug it into our second derivative. So we'll plug in 0 and we'll plug in 2 to our second derivative. Now if I plug in 0, I'm going to get a positive number. And whenever you have a positive number, we're not going to draw a positive slope, we're going to draw a concave up. And whenever you plug in 2, you're going to get a negative answer. And so that means it's going to be concave down. And so yes, the point where they connect would be a point of inflection. So we have the point of inflection is x equals 1. The interval where it's concave up would be from -infinity up to 1, the left side. And the interval where it's concave down would be from 1 to infinity. Okay, and that's that. So those ones will have just polynomials. I won't be throwing any of the other options at you. All right, let's move on. Yes, the optimization problem. So these are going to be worth a little bit more points because these other ones we haven't really had any quizzes on or anything, so I want them to be a little bit heavier. So we have an optimization problem. You're going to get only one question, but I'm giving you 3 types on your study guide just so that you're ready for all 3 types because you could end up with any 3 of these. You get 1 point for your primary equation, 1 point for your secondary equation, 1 point for doing the substitution correctly, and then finally 1 point for finding the minimum or maximum that they're asking for a total of 4 points. So for number 8, we have this question here. It says some engineers are designing a box-shaped aquarium with a square bottom and the aquarium must hold 500 cubic feet of water. The question is, what dimensions should, let me shrink this because it's a little bit, oh, also says it has an open top. That's an important thing to pay attention to. What dimensions should they use to create an acceptable aquarium with the least amount of glass? So first of all, I'm going to draw a picture because we're talking geometry here. The bottom's a square, so I'm going to call the bottoms both x's, right? But the height could be different, so I'm going to call the height x. Now, the primary equation is the one that we're trying to minimize. And what I'm trying to minimize is the amount of glass that we would be using. Now, first of all, we would need glass on the bottom. So the area of the bottom would be x times x, which is x squared. So we would need x squared amount of glass on the bottom. And each lateral side has an area of x times h. So, and there's 4 sides. There's the left side, the right side, the front, and the back. So we have 4 xh's. And putting all that together, we have our total surface area. You'll notice I didn't count the top, and the reason why is because the top's open. There is no glass on the top, so we're not going to include that. So that's my primary equation, which represents the surface area. That's the thing I'm trying to minimize. I want to have the least amount of surface area possible. Now we want my secondary equation. The secondary equation is the one that limits your possibilities. And in this case, my limitation is the fact that the volume that this thing holds has to be 500 cubic feet. How do you find the volume of a cube? Well, you do length times width times height. So that's x squared h. And I know that that volume should be 500 cubic feet. So there's my limiting secondary equation. So that's 1 point here and 1 point for that. So if you can find your 2 equations, then that gives you half the credit. All right, from there, we're going to move on to the substitution method. And when you're doing the substitution method, you're going to take your secondary equation first, and you're going to get one of the variables by itself. Doesn't really matter which one you get by itself, other than the fact that say just make sure it's one that makes everything a little bit less confusing. So in my opinion, it's a lot easier to get h by itself. That way, I don't have to take any weird square roots or anything like that. So now I can see that h is equal to 500 over x squared, and we're going to substitute that in for the h in the other equation here. So s is equal to x squared plus 4x times 500 over x squared. All right, and we do want to simplify this a little bit. So first of all, 4 times 500 there is going to be 2,000. And then x cancels one of the x squareds out on the bottom, leaving me with just x. And I know that I'm going to be wanting to take the derivative of this in my next step, so I'm going to rewrite the equation a little bit so that it's a little bit more derivative friendly by changing it from 2,000 over x to being 2,000 times x to the negative 1. And so that's the end of step 3, and that would be worth another point. All right, once you have your substitution method done, we're ready for step 4, which is to go ahead and find the derivative of that expression. Using the power rule there. And then we're going to set that equal to 0. I'm going to add 2,000 x to the negative 2 on both sides of the equation. So that way I get 2,000 x to the negative 2 equals 2x. It might also help if I rewrite this as 2,000 over x squared equals 2x. And then if I multiply both sides by the x squared, we can get that off the bottom. And have 2,000 is equal to 2x cubed. If I divide both sides by 2, and then if I take the cube root, I end up with x equals 10. So I got x equals 10. Now the question is asking us to find the dimensions. That means the length, the width, and the height. Well, the length and the width are the same. They're both x, so we have that. So we have the length. We also have the width. They're both 10. But we need to find the height. So to do that, I would say come on back to your secondary equation, plug in the number that you know, and solve for the one that you don't. So 10 squared is 100, and divide both sides by 100 and you get 5. And so my height is 5. And there's my final answer. So 1 point for primary, 1 point for secondary, 1 point for substitution, and then working out your answer to get to the end is your final answer. You got to show all your work, of course, but that's how I'll be distributing the points. That's one type of optimization problem you might receive. Or you might get this one. This is the cryptography question. A cryptography expert is deciphering a computer code. To do this, the expert needs to minimize the product of a positive rational number and a negative rational number. So my primary equation is going to be a product, which is a positive rational number being multiplied by a negative rational number. And then it tells us that the positive number is 5 greater than the negative number. And that tells me what my secondary equation is going to be. My positive number is 5 greater than my negative number. Substitution. Since I already have a letter by itself, I can replace r with 5 plus n in my primary equation. So if I replace this r with 5 plus n, I would have the following. And we do want to distribute that in there, so we get 5n plus n squared. Step 4, we want to take the derivative of this thing and set it equal to 0. So e prime is equal to 5 plus 2n. We want to set that equal to 0. And then we want to solve. If I subtract 5 and divide by 2, I get my negative number, which is negative 5 halves. And then, if you want to find your positive rational number, once again, you're going to take your first answer and go back to your secondary equation, and you're going to plug in the number that you know to solve for the one that you don't. Common denominator here. Positive 5 halves. So I've got n equals negative 5 halves and r equals positive 5 halves. But the question's actually asking us what's the final product. So they want to know what is the actual product of these two numbers. They don't want to know what's the negative. They don't want to know what's the positive. They want to know what's the product of those two things. In other words, if you multiply them together. So the product would be positive 5 over 2 times negative 5 over 2, which is going to be negative 25 over 4 is your final answer. So that's another type of optimization problem you can expect to see. Or you might see the pigpen question that we talked about. And there's two types of these ones. There's the one where you can have it built next to a stone wall that already exists, or it could be one where you have two rectangles that are similar right next to each other. They're both in the notes, so either one is fair game. This one in particular is the one where they're building it up next to a stone wall. So a farmer wants to construct a rectangular pig pen up against a stone wall. And so we have a width and a length there. Now, what dimension should the farmer use to get the largest possible area, given the fact that he's only allowed 200 feet of fencing? Well, the primary equation is the one we're minimizing. we want to, maximize. We're trying to maximize the area. So how do you find the area of a rectangle? The area of a rectangle is length times width. The secondary equation is the limiting factor of all this. And the limiting factor here is that I'm only allowed to use 200 feet of fencing. So I know that W plus L, or in other words, 2W plus L, it has to equal 200 feet of fencing. Now for the substitution method, we want to get one of our variables by itself. So I'm going to get the L by itself. I'm going to subtract 2W on both sides, and that would give me 200 minus 2W. And that's what I'm going to plug in for L into my primary equation. And we do want to distribute. All right. Now we move on to the fourth step, which is to find the derivative. Set it equal to 0. That's how we find our max. And we solve. If I subtract 200 and divide by 4, I end up with W equals 50. And if you want to figure out what the length is, then once again, we're going to come back to our secondary equation. We're going to plug in the one number that we know now to solve for the one that we don't know, which is L. So I know that W is 50. And subtraction gives me 100. So my length is 100. My width is 50. All right. So there you guys have it. Those are your optimization problems that you can expect to see on our test. All right. Let's go ahead and take a look at this type of question. You'll see one of these two. It's only worth 1 point. On this particular problem, I give you some information. And then I ask you which of these things are true. Okay. So I would just say turn it into a graph. This first one is a point, over 1 up 5. So I've got a point right there. That tells me my slope. So my slope at x equals 1 is 0. So I know that there's a horizontal tangent line there. And here I see that my second derivative is 4. Now I don't care about the number. What matters is the fact that that's a positive number, which means that my second derivative is positive. And when your second derivative is positive and your slope is 0, you have a relative minimum there. So my graph would look something like that. Now there could be more to the graph, but that's all that I know is what I have right there. So is x equals 1 a critical value? Well, a critical value is any time the derivative equals 0. And my derivative does equal 0 at 1, so that's true. A critical value is also where your derivative is undefined. But in this case, that's irrelevant. Next, is x equal 1 a relative extrema? Yeah, looks like a relative minimum, so that's true. Is it an absolute extrema? No, not necessarily. We don't know that for sure. There's no reason to assume that. Just because it looks like it's the lowest there doesn't mean that it doesn't go lower somewhere over here, because they didn't give us any information about anything over here. We only know stuff about one single point. So I don't know if that's an absolute extrema or not. Next, for all x less than 1, which that means to the left, f is increasing. Well, look at the graph. Does that look like f is increasing? No, it doesn't look like f is increasing to me. So I would say no. That is false. And so, and I wouldn't say, actually, I'd go back to number 3 here. I wouldn't say that's false. We would just say we don't know. But the question is what must be true? 3 could be true, but we just don't know if that's true. So the only ones that we know are true for certain are 1 and 2. So the answer would be option. Now you're only going to have one question like that on your test, but I'm giving you 2 here just for the sake of practice. So let's do another one. f of 5 equals -2. So that's a point. My slope is 0 once again. And now that's a little bit confusing right there. They tell me that my second derivative is 0. Well, that doesn't tell me much. It doesn't mean that my graph is. What it means is that my graph is neither concave up or concave down at that point. So gosh, what does that mean? If it's not neither, well, that would mean maybe it's switching at that point. That's a possibility. But technically, it is. It is possible though for a graph to actually be concave up, but not register as concave up whenever you do the second derivative. So this is something that we talked about in our class. We talked about how if the second derivative is 0, it's inconclusive. We just don't know. That doesn't mean anything to us. So this is useless. It tells us nothing. So all I know is that I've got a point there, and the slope at that point is 0. That's all that I really know. So is x equals 5 a critical value? Yeah, that's still true because critical values are where the derivative equals 0 or the derivative is undefined. So that's true. Is it a relative extrema? Well, it's hard to say. It could be. You know, it's possible the graph looks like this. That is possible, even if the second derivative is 0, in which case it would be. But another way you could have it equal 0 is if the concavity is switching, in which case it's not. So we don't know if it's an extrema or not. Is it a point of inflection? We don't know. The concavity would have to be changing, and we really don't know what's going on the left and right. For all x greater than 5, so everything on this side, is f increasing on this side? That's the two ways I drew it so far, but I guess I could have drawn it like this too. That's possible. So we don't really know. Anytime your second derivative is inconclusive, you're kind of lost a whole lot of information. So the only thing that I know for certain is that A is option 1 is true, the critical value. All right, moving along. We're going to see quite a few of these different types of questions. Going to be, let's see, 4 types. Number 13, I give you f, and I ask you to find a graph of f prime. Number 14, I give you a graph of f and ask you to find me a graph of f double prime. Number 15, I give you a graph of f prime and ask you to find a graph of f. And then on number 16, I give you a graph of f double prime and ask you to find me a graph of f. So those are the 4 types. And I threw an extra one in here that involves asymptotes because those are a little bit weird, and we talked about those in class. Those are the kinds that you can accept to see, though. So let's go ahead and take a look at this one. So I've got a graph of f, and I'm being asked about f prime. So in other words, the slope. So what do we know about the slope of f here? Well, as I can see, the slope is positive everywhere, except for maybe right here. It looks a little flat to me. So it looks like the slope is positive everywhere. Because this graph never stops going in an upward direction. But I do see one exception, and that's right in the middle. That looks like a really flat line right there to me. And that looks like a flat slope. So I would say that f prime equals 0 at x equals 0. So we're looking for a first derivative graph where it's always above the x-axis, except right at 0. And at 0, it's actually touching the x-axis. Which one of these graphs is always above the x-axis, but touches the x-axis right at 0? Well, this one's not always above, and this one's not always above, and this one's not always above. And there's our answer. And it looks a little bit off to me. Should be touching the x-axis, maybe right about there. Or maybe it's because I misjudged where they had the flat slope. Maybe the flat slope was a little bit further over this way. And so that's why it's touching the x-axis a little bit further over to the left. But either way, it doesn't really matter. It's always above except for one place where it actually does equal 0. And so I'd say there's our answer for that one. I'm going to take a look at 14. Now this is a graph of f, and we're being asked to find a graph of f double prime. And that has to do with the concavity. So how would you describe the concavity of this graph? Well, f is always concave up on this graph. And if f is always concave up, that means that f double prime is always greater than 0. And if double prime is always greater than 0, that means the graph of f prime must always be above the x-axis. So which one of these graphs is always above the x-axis? That would be C. All right, let's take a look at another question here. This time, I'm giving you a graph of f prime, and I'm asking about f. So this is a slope of f. So here, when you're looking at a graph of f prime, anywhere where f prime is above the x-axis, f will have a positive slope. So, since f prime is above the x-axis, from negative infinity to, looks like it stops right about here at negative 1. And from, I don't know, a little bit after 1, like we'll say 1.8 to infinity. Since f prime is above the x-axis on those two pink intervals there, f will be increasing on those intervals. So let's look at our graph, and let's see if we can find a place. Which one of these graphs are increasing from negative infinity up to about 1.8? Let's see. Now, from negative infinity here, that's decreasing. So that's no good. We don't want that one. This is also decreasing at negative infinity, so we don't like that one. This is increasing until we get to about, maybe, that could be about negative 1. And this one's increasing starting at about 2. Now this one's increasing up until about maybe negative 1. But it also needs to be increasing from 1.8 up into infinity. And on this side, it's negative, so that's no good. So this is the one that's increasing on the left and on the right. It has a positive slope on the left and on the right. You can also have done this by, instead of looking at where it's increasing, you could have looked at where it's decreasing. Since f prime is below the x-axis between negative 1 and 2, or 1.8, we're looking for a graph that's decreasing between negative 1 and 1.8. And so the answer for this one would be C. All right. So for this next question here, I'm telling you f double prime is what we're looking at. And I'm asking you to find a graph of f. Well, f double prime represents the concavity. So since f double prime is above the x-axis from negative infinity up to 1, that means that f double prime is greater than 0 on that interval. And if f double prime is greater than 0 on that interval, that means that f is concave up on that interval. So which one of these graphs down here is concave up from negative infinity up to about 1? That looks like this graph to me. That looks like that one's concave up from negative infinity up to 1. I'd say our answer there is B. Right, and last one we'll look at like that. Number 17. All right, so vertical asymptotes. Here's how this works. I'm going to work my way backwards from the second derivative to the first derivative all the way up to the original graph. So we're going to do this one at a time. And the way it works is when you have these vertical asymptote problems like this, the left side is going to stay the same, but the right side is going to flip every time you change from one derivative to another. And so whenever I change from f prime to f, the left side stays the same, but the right side's going to flip. So I'm looking for the graph that looks like that. So that would be option D. And that's just a shortcut. Now, I mean, you can kind of look at it and tell, like, okay, to the left it's an increasing slope, and to the right it's an increasing slope, and kind of figure it out that way. But the shortcut is a little bit easier to go with on those ones. So, all right, last question here. This is a multi-part question. Now here I've got A through G. Now on your test, I'm only going to give you 3 questions about the graph, but each one's going to be worth 2 points. You get 1 point for the answer and 1 point for your explanation. So altogether, this question on your exam will be worth 6 points. Okay, so let's begin here. Part A says, identify the intervals where f is concave up and increasing. Justify your answer. So before I begin, it might be good to just list some facts. So first of all, we want to identify the fact that this is a graph of f prime. So that's very significant. You have to understand that you're looking at a graph of f prime. Okay, so here's what we know. If f prime is above the x-axis, that means f is increasing. Contrarily, if f prime is below the x-axis, that means f is decreasing. If f prime touches the x-axis, that means that f has a horizontal tangent line, which is very often a relative min or max. Anytime you've got a horizontal tangent line, you very well may have a relative minimum or a maximum where it touches the x-axis. So that's one thing that we know. So based on this graph, which is a graph of f prime, if it's above, f is increasing. If it's below, f is decreasing. If it's touching the x-axis, that is possibly a relative minimum or a relative maximum. Right? What else do we know, though? Because here's what we know about this. If this is the graph of f prime, then that means that f double prime is the slope of this graph. So f double prime is the derivative of f prime, which means that f double prime is the slope of f prime. So, for instance, whenever this graph has a positive slope, that means that f double prime is positive. Now I'm running out of space here. Just a sec. All right, there we go. I just shrink it to make more room for myself there. All right, so let's say that again. So remember, f double prime is the slope of the f prime graph. So that means that if f prime has a positive slope, that means that f double prime is positive, which means f is concave up. Because if the second derivative is positive, that means f is concave up. Contrarily, if f prime has a negative slope, that means that f double prime is negative, which means that f is concave down. And finally, if f double prime has a zero slope, well, actually, let's put it this way. If f prime changes from positive slope to negative slope, well, that means that f double prime is changing from positive to negative, because f double prime is the slope, which means that this is a point of inflection. Okay, so there's a lot of information to keep in mind here, but there it is. So nice little bit of information here to keep in mind as we do this exercise. So let's begin. This problem is asking us to identify two things happening simultaneously in part A. It's asking me to find where f is concave up and where f is increasing. Well, f is concave up when this graph has a negative slope. Because when this graph has a negative slope, that means the second derivative is negative, which means that f is concave. Oh, that's concave down. My bad. Back it up. Concave up's right here. So f is concave up when f prime has a positive slope. Because when f prime has a positive slope, f double prime is positive, which means that f is concave up. So there's that. But they also, so let's look for that first, and then we'll get to the next part. So let's look for where f is concave up. So we're looking anywhere where f prime has a positive slope. So like from here to here, that's a positive slope. And also from here to here, that's a positive slope. So on those two intervals, f would be concave up because f prime has a positive slope, which means that f double prime is positive, which means that f is concave up. Okay. Next, we want to find where f is increasing. Blasted, I keep trying to change the color and it won't let me. There we go. Now I want to find where f is increasing. Well, f is increasing anytime f prime is above the x-axis. So, just looking at these spots that I've already highlighted, well, I guess we could do them all. So, f prime is above the x-axis on this entire green region that I'm highlighting right now. Pretty much from -4 all the way up to 3. It's above the x-axis. But remember, I'm looking for the places where it's concave up and increasing. So I want both happening simultaneously, which means I don't care about this area right here, or this area, or this area. I want the place where it's green and purple, and I also don't care about this down here. So right here are the regions where it's green, representing concave up, because it's f prime is above the x-axis, and it's purple because it's sloping upwards. F prime is sloping upwards, which means that f is also concave up. So that one, our intervals will be from -4 to -3. And then from 1 to 2. All right, so now I'm going to do part B. Let's do part B. Now, I hope you guys don't try to memorize this stuff. I hope that this just makes sense. Like, I didn't memorize this. I just wrote this out because it makes sense. If f prime's above the x-axis, that means that it's positive, so f is increasing. So I hope that you guys know that. If you want to try to memorize it, you can, or write it down. You can use it, but remember on your AP exam, technically that you're not going to be able to use stuff. Well, who knows? You might be able to if they still do it at home test. We'll see. But hopefully this just makes sense. I would hope that you guys could derive all this stuff just based on the facts of what we know. If you can't, then I would encourage you to really think about these and be able to reproduce those from your own mind. But let's go ahead and do part B. So we're looking for the interval now where two things are happening, where f is concave up and also where it's decreasing. Didn't change colors again. All right. So let's look for where it's concave up first. Where in my list here do we have concave up? We've got f is concave up right here, which means that my graph will have a positive slope at that point. Because when f prime has a positive slope, f double prime is positive, because f double prime is the slope of f prime. And if f double prime is positive, that means that f is concave up. So where does this graph have a positive slope? Well, it's the same question as last time, actually. We have the same stuff. It's this one and this one. It's the second part that's different this time. Now we're looking for where f is decreasing. So where is f decreasing? F is decreasing when my graph of f prime is below the x-axis. Now that happens in only one spot, and that would be right here. Actually, two spots, right there and also over here. So those are the two places where my f prime graph is below the x-axis. Now I want these things to be happening simultaneously, though. I want green and orange to be happening simultaneously. And the only place that happens is with what's left there. So from -5 to 4 would be our answer for part B. And you know what? I've been being a bad boy. I didn't write my explanation for part A. I guess I can go back and do that. But here, I'll do it for part B, because you guys do have to give your explanation for this. So I would say here, f is concave up since f double prime is greater than 0. I'm sorry, less than 0. Because this is for part B, it's supposed to be concave. I'm screwing that all up, aren't I? Just a second, sorry, I'm having some technical difficulties. All right, let's try that again. All right, so f is concave up because f double prime is greater than 0. And f is decreasing because f prime is less than 0. Now you don't need to get into the things talking about the slope or the below or above the x-axis. That doesn't matter. All that matters is stating the facts about f prime and f double prime. Okay. So if we go back now to part A, I'm going to delete this if it'll let me. So I'm going to go back to part A now and put the rest of my answer. We said it was concave up and increasing on the following intervals. From -4 to -3, and from 1 to 2, since f is concave up when f double prime is greater than 0, and f is increasing when f prime is greater than 0. And in this case, that was because it was above the x-axis. So that's for part A. All right, let's go ahead and do part C. Part C is asking us to identify those intervals where f is concave down and increasing. All right, let's start with concave down. F is concave down when f prime has a negative slope. So looking at our graph, where does f have a negative slope? I see f having a negative slope here, here, and here. Next, we want to find where is f increasing. F is increasing anytime f prime is above the x-axis. So that would be here, here, and here. And the only part that would be excluded that we've already highlighted purple would be this part down here. So final answer for part C then is going to be the interval from -3 to 0, from 0 to 1, and the interval from 2 to 3, since f is concave down when f double prime is less than 0, and f is increasing when f prime is greater than 0. And so that would be our answer to part C. All right, let's go ahead and take a look at part D. Identify the intervals where f is concave down and where f is also decreasing. Well, let's start with concave down. F is concave down anytime f has a negative slope. And so that happens here and here and here. Same spots as last time. And now we want to know, where is f decreasing? F is decreasing anytime f prime is below the x-axis. So that would be over here on the left and over here on the right. And so the only places where the blue and the green are happening simultaneously would be on that little wing on the right side over there. So that would be from 3 to 4, it looks like. And there you go. That's the answer to part D. Alrighty. Let's move on to our next question. Part E. Identify the relative min of f on the interval from -5 to 4. Now that's just the entire graph. So here's what we know. We know that f has a relative minimum when f prime goes from negative to positive. So where does f prime go from negative to positive? Well, f prime is negative here, and it's positive here, and then it's negative here. Oops, wrong color, my bad. So the green spot is where f prime is above the x-axis, which means that f prime is positive. And then the blue parts are where f prime is below the x-axis, and that's where f prime is negative. So at what point does the slope change, or f prime change, from negative to positive? Well, I would say that there's only one point where that happens, and it's right here. At that point, we go from being below to above. This point over here goes from above to below. Remember, we always think as we go from left to right. So if I'm moving from the left to right, this is the one that goes from negative slope to positive slope. And so that point right there is a point where we'll have a relative minimum. And so we would say f has a relative minimum when f prime goes from positive to negative. This happens at x equals -4. So that's our answer to part D. Let's go ahead and take a look at part E. Part E says I'm sorry, that was part E. Let's do part F then. Identify the relative, this was supposed to say maxima, so I'll have to fix that. Identify the relative maximum of f on the interval. Well, the opposite of the last one, right? F has a relative max when f prime changes from positive to negative. And this happens at x equals 3. Right here. Because to the left of that point, f prime is above the x-axis, which means it's positive. And to the right of that point, it's below the x-axis, which means f prime is negative. And so when f prime changes from positive to negative, that means you have a relative max. So f has a relative max when f prime changes from positive to negative, and this happens at x equals 3. All right, final thing we'll look at is identifying any points of inflection that may exist. All right, a point of inflection happens when f changes concavity. F changes concavity whenever f double prime changes signs. Okay, so where does f double prime change signs? Well, from our little notes here, f double prime changes from positive to negative anytime f prime changes from a positive slope to a negative slope, or vice versa. I should have, on number 7, I should have said that it could go either way. It doesn't have to be from positive to negative only. It could be from negative to positive. The point is that the concavity is changing. So anytime f double prime changes its signs, that means that f prime is changing its slope. So a point of inflection is where f changes its concavity. This happens when f double prime changes signs. Now in our graph, that happens anytime the slope is changing. I see the slope of this graph changing here because to the left we have a positive slope and to the right we have a negative slope. And I also see that happening here because to the left I see a negative slope and to the right I see a positive slope. And I also see that here. To the left I see a positive slope, but on the right I see negative. I see 3 places, 3 points where the slope of my f prime graph is changing. And when the slope of f prime changes, that means that f double prime is changing signs, which means that f's concavity is changing. So -3, x equals -3, 1, and 2. So a point of inflection is where f changes concavity. This happens anytime f double prime changes sign. On our graph, that's where the slope of this graph is changing from positive to negative or vice versa, which is these 3 points, -3, 1, and 2. Okay, and that'll do it. So I will go ahead and make one little modification here to my little notes on the side. Instead of saying positive, negative, I'll put f prime changes from a positive slope to a negative slope, or from a negative slope to a positive slope. When this happens, f double prime changes its signs. Which means f is changing its concavity, which indicates that this is a point of inflection. So I'll read it one more time. If f prime changes from a positive slope to a negative slope, or from a negative slope to a positive slope, when that happens, f prime is changing its signs, which means that f is changing its concavity, which means that this is a point of inflection. So there you guys have it. Summary of everything there. So that's a lot. Remember, you get 1 point for correctly identifying the points or the interval. You also get a point for your explanation, and I showed you how to write your explanation for all of them here. And that's that. So your test will be much shorter than this one, but I just wanted to give you guys a whole lot of practice so you can get ready for your test, ready to rock it. So anyway, we'll see you guys on test day. Good luck.